actually get a thumbs up on that screen?
Yeah,
we can see
it.
Okay, great. We had been considering this circuit for decoding Hawking radiation. And the basic concept was that Alice throws her qubit into this black hole here, which is represented by some unitary operator that should scramble if it's a black hole. And Bob can attempt to decode this information if he has another identical black hole that he has entangled with Alice's via a shared EPR pair. And the general protocol involves projecting these two qubits that are shared between the two black holes onto an EPR pair after the scrambling operation. And roughly speaking, we gave an example of how at least sort of the classical information could end up over here in the case where this was not a completely scrambling random unitary, but just a C0 gate. And the intuition that we had at the end of last lecture was that we could arrange a situation where the only way that these two qubits would end up in that EPR pair that they started in, 0, 0 plus 1, 1, would be if either both of these control qubits were 0 or both of them were 1, because we need to either flip both qubits or flip neither qubits in this EPR pair for it to end up back in the same state. So that was kind of the intuition for how this process of projection can kind of essentially conditioned on that projective measurement, we can have information that was previously here in Alice's state end up over here in Bob's possession. Okay, so maybe questions about where we stopped before I kind of show an example of an experiment?
So just to have the intuition right, so you can decode the information that comes out of Hawking radiation as long as you have another black hole to help you with.
Yes, but you said you can, right? You can, yeah.
You can.
Exactly, which which needs to be entangled with the first one, which you can do by sort of having this EPR pair that's split between the two.
Okay, thank you.
And so an important point about this was that with what fidelity you can do this decoding depends on how well this scrambles. And in the one example I gave where it's just the C0 gate, it kind of does the right thing in one basis. The fidelity will be, where do we write that? So the fidelity would be high for just like if it happens to be a 0 or a 1, but for a generic qubit, it's not perfect. But if this scrambles, then kind of irrespective of the basis, this can teleport well. And so the neat thing about this is we said sort of the probability of projecting onto the EPR pair will go down, and actually is a measure of the out of time order correlator decaying. But measuring something decaying in an experiment is sometimes not sort of a smoking gun for scrambling, because there are lots of sources of decoherence that can make things decay. And so a nice thing about this protocol is that you can actually have sort of a positive signal, which is that actually this fidelity increases. And so now if I, actually, I wonder, let me see whether I can do this directly on my, I can do this on my iPad. I don't have to switch screens. Okay. So there were now a few different experiments that, or two experiments in particular, that use this protocol in either trapped ions or superconducting qubits. And I'll just show some examples of the measurement that was done in this trapped ion system, where essentially they have, this is kind of what their experiment looks like. There's this chain of, in this case, 7 ions that they did this demonstration with. And they can sort of locally address them with some laser beams in order to implement these gates. Similar to things I've talked about before, the way that they have their qubits interact is via sort of the motional mode. So there's some Coulomb interaction, and they can have the motional modes mediate interactions between their ion qubits. Okay, and so in this case, this is the circuit they built. They actually have kind of 3 qubits going into each of the black holes. but actually just projecting on one pair here. So this is sort of the pair, right, that starts out as an EPR pair, and they project onto this do a projective measurement and ask, conditioned on finding this in an EPR pair, what's the fidelity of teleporting Alice's qubit to here? And they can also ask, what is the probability that they, in fact, this projective measurement succeeds? And so they actually do kind of a comparison of what happens if they have a scrambling operation, that's kind of illustrated here in blue. There's some unitary involving these 3 qubits. And the degree to which it scrambles is parameterized by something they call alpha. 0 would mean not scrambling, 1 would mean scrambling. And I won't go into the details of what's in this circuit, but you can imagine there's a way of tuning sort of how random this is. The other case that they consider is something where they sort of want to do an identity operation. So we gave that example last time, right? We said if U is the identity operation, then the teleportation is no better than just randomly putting some quantum state here, 50% fidelity. So they sort of make an identity operation, but they want to actually allow for sort of see what would be the effect of kind of experimental imperfections. So they make a fancy version of the identity operation. So it turns out if you, in addition to sort of doing nothing, if instead of doing nothing, you do an X rotation on one qubit, a Z rotation on one, and a Y on another, that actually should end up being equivalent to the identity operation if there's no rotation. But if there's a small rotation, then this could actually this is sort of mimicking some sense of decoherence. And so when they do this experiment, they can ask, what is the fidelity of decoding? And what is the probability of actually measuring? So what is, first maybe you say, what is the probability of actually measuring this EPR pair to be in the state it started in? And the second one is conditioned on getting that measurement outcome. What is the fidelity of the decoding? Okay, so the probability is shown on the left. For these 2 cases, the one that's sort of an imperfect identity operation, as we increase theta along this axis. Oh, you also have this little toolbar hiding the slide. Okay, so as we increase theta, can I point and not have the toolbar out of the way? Okay, no, sorry. Okay. I think you can see what I'm talking about. So if I talk about the left image, as they increase this mismatch parameter theta that says how far is it from the identity, the probability of successfully measuring the desired EPR state goes down. And that's actually a measure of this out of time order correlator. But this isn't because of scrambling in this case, right? It's just because of some imperfection in the, some decoherence, essentially, some imperfect operations. But also, and similarly, as they increase the scrambling parameter in the left plot, right, they also see this probability go down. And so the point here is it's not so easy to distinguish the scrambling from the imperfection just from seeing some quantity decay. So in the right plot, they instead look at the fidelity of the decoding. And there, not surprisingly, if you just have this sort of imperfect identity operation, then it's always sort of just 50% fidelity, which is what you would get if you randomly guessed the quantum state to put into qubit 7. But if they actually have an operator that scrambles, as you increase the amount of scrambling kind of by ramping alpha from 0 to 1, they see the fidelity of this teleportation go up. And so that's here, this increase in fidelity shows that this isn't just decoherence causing this correlation function to decay, but it really is the process of scrambling. So that's kind of a neat like positive signature that, first of all, a positive signature of the scrambling, but also kind of a toy model demonstrating this idea of decoding the Hawking radiation. So yeah, and so this has now again been done in a couple of different physical systems. I see someone hiding their video. So is there a question?
You answered my question.
Yeah.
Sorry.
Yeah.
Thanks.
Okay, perfect. Good. So again, so this is kind of, it's a few qubit system. There was the question earlier, can't you calculate this? Yes, you can calculate it. But nevertheless, actually having sort of the level of experimental control to do this with even just a few qubits is sort of really an important starting point for asking, could you scale this up? Could you do this also with sort of more complex many-body systems? One thing you might want to do, so far in this experiment, we said that kind of the entanglement between the two black holes has the form of an infinite temperature thermofield double state, right? So the thermofield double would be each state looks thermal, but the state of the entire system is pure. One of the things you might want to be able to do is also study, for example, finite temperature systems. And so one other thing that's kind of a nice experiment that was recently done in this same group, which is the group of Chris Monroe, was to demonstrate how you might go about preparing things that essentially this type of a thermofield double state. And the approach that they take is, so I've written this down here, right? So maybe you would like to prepare two entangled copies that look like they each have effectively some temperature beta, right? So these are just different eigenstates of the system. J labels the eigenstate of the system, E sub j is the energy. If I had the state like this, then each kind of copy would look thermal by itself, but the state as a whole is pure. So this is an experiment where, okay, each copy of, it's two copies of a 3-qubit system, right? There are 6 qubits in total, so not a huge system, but what they are able to do is actually initiate the system in a set of EPR pairs that realizes kind of the infinite temperature version of this, right? Beta is 0. But then they can actually kind of cool this state. And the way that they cool the state is actually they implement kind of a variational algorithm, which is to say they have, so right, this is their initial state. These kind of bonds here are indicating EPR pairs, right? So this is one copy, this is another copy of the system, they're entangled. So this sort of says, okay, so we start with this infinite temperature thermofield double state. And then they have some sequence of gates that they can apply. And without going into too much detail here, the basic idea is that if you have some kind of parameters you can vary in this subsequent circuit, you can try to kind of steer the system to a lower energy state. So this is sort of a hybrid quantum classical algorithm where you implement some circuit here, you can measure, if you do multiple repetitions of the experiment, you can measure the expectation value of the energy, which just has, in this case, it's a transverse field Ising model. They can measure the expectation value of the energy by looking at essentially spin correlations. And then they can feed back, change their variational parameters, and optimize this circuit to try to bring it to kind of a lower, to effectively a low temperature state. And so that's kind of one approach that's being explored to saying, could you sort of implement these same types of protocols, but with finite temperature states? Questions about that?
So I have a question. Why don't you just sorry, I'm a theorist, but can't you just like compute what you should put into, what parameters you should put in, and then just put those in? I guess I'm confused by the feedback on this.
Yes, yeah. For 3 qubits or 6 qubits for the double system, you can. So I think the point is more if you wanted to scale this up to a regime where you can't compute what parameters would take you to this state, you can nevertheless measure the expectation value of the energy, because that's just like if my Hamiltonian is just sum over ij, jij, sigma I, sigma j, plus h, sum over I, sigma x sub I or something, right? I have this transverse field Ising model, and I can easily measure the expectation value of the Hamiltonian by implementing the same circuit a bunch of times and looking at correlation functions, right? I need some 2-body correlation to measure the Ising component and the interaction term and the average magnetization along x to measure the transverse field term. And so then I can basically, steer myself towards lower energy that way. So that's basically the concept. And that idea is, that idea comes more from the sort of quantum computing direction. So how do you maybe solve some optimization problem that's encoded in an Ising model? And this is known as the QAOA algorithm in that context. And here they're using it actually, they did a couple of things in this paper. So they used it to prepare low energy states at a critical point in this model, but also to prepare this thermofield bubble state. So, yeah. Cool. Other questions at that point? Okay. So this is kind of, yeah, it's sort of like using a quantum computer to do this. And there's another sort of, you might want to ask, is there sort of a way that's not sort of implementing these very specific quantum gates? And it turns out that it's been pointed out, I mentioned this, I think, in answer to a question earlier this week, that actually quite generically, if I, oh, actually, sorry, I want to show this first. So if I have kind of a system where I have, let's say, two systems that are identically prepared, and they're kind of coupled to each other, it's actually very natural to end up in a situation where if I have, unitary evolution, each half of the system alone looks thermal, but the entire system is in a pure state. And so it turns out that it's actually fairly natural in systems that obey what's called the eigenstate thermalization hypothesis, that sort of typical eigenstates locally look thermal. It's actually very natural that this type of a state would kind of arise even without kind of implementing a quantum circuit to make it. So this is actually an example of an experiment that was done with ultra cold atoms trapped in an optical lattice. And so here there are basically 6 atoms optically trapped, and they can hop between sites. And if they're both on the same site, these are bosons, and if they're both on the same site, they will have some interaction. So this realizes a Bose-Hubbard model. And in this experiment, it was actually possible, and I'll say in a moment how, but it's actually possible to measure entanglement entropy or Renyi entropy as a function for subsystems, and to ask kind of what is the entropy of this subsystem or a larger subsystem. So this is a plot basically of the entanglement entropy, or sorry, the entropy of a subsystem as a function of the size of the subsystem that you select. And so if you select the subsystem to have size 0, then the the entropy is 0, not surprisingly. But also if you take the entire system, that's this point over here, then the entropy is 0 because it's prepared in a pure state, essentially, to the best of experimental capabilities. And but if you cut it and you look at the entropy for some subsystem, like for example, half the system, that's higher. And okay, the gray line is indicating what it would be for a thermal state. It's not precisely thermal for the half cut, but it's still kind of approximating something like this. If you sort of think of each half of these systems, each half is sort of in let's say an approximately thermal state without doing any sort of fancy preparation. It's just having these coupled sites of a Hubbard model. So one thing that's I think kind of cool about this is how do they actually do this measurement where they're measuring the Renyi entropy of the system? Because quite generally, sort of, the fact just being able to measure entropy, measure entanglement entropy is something that, it's something that's convenient to calculate, but not actually so easy to measure in experiments. And so just to be clear, so for example, if I take this, this half cut here and I ask what is the Renyi entropy of one side of the system, that's telling us about also entanglement entropy between the two halves. So how do they do this? Actually, does anyone here know how they did this or have an idea how you could do that measurement in this experiment? No, okay, fine. So let me just show kind of a little bit more of a picture of what they do. So it turns out this is again something where they take advantage of being able to prepare 2 identical copies of a physical system. So that turns out to be kind of a powerful trick. So they start, in this case, with an array of, again, it's an optically trapped atoms that's prepared in a Mott insulating state, which is due to the influence of interactions, the atoms sort of organize themselves in a situation with a single atom per site. So that's just a way actually of preparing a nice clean system with 1 atom per site. They have some control over the depth of the lattice that's separating these atoms. So that gives them the ability to sort of partition the system and think of, let's say, a row as an independent system, or to actually couple two rows. So that's an important tool here. So in this case, they kind of initialize this as two independent chains of 6 atoms each. And by lowering the lattice depth, they kind of quench on tunneling. So the atoms can start to tunnel between sites in each of these copies of the system. And then their trick for measuring entanglement entropy in this system involves essentially doing some interference between these two systems. So turning on, so freezing the dynamics along the chain, but actually turning on a coupling between the two chains. And that's kind of illustrated here, turning on a coupling between the two chains. Okay, and that interference experiment where you interfere the two copies of the system can give you information about entanglement. So to give kind of a flavor of how that works, let me actually just write for a moment. So the intuition kind of is that, so they have, the experiment, they have, just sketch this one more time, they have these two chains, each of them has 6 sites. They should be identical. I'm not good at drawing them, so they look identical, but imagine that they're identical. It's just like that. And as to kind of get a sense of how you can measure something about entanglement in the system, it's useful actually to first think about a really simple example. So basically what we're going to do is we're going to turn on kind of pairwise couplings between these sites to interfere our two copies of the system. It's kind of so essentially I can think of this as if I call this system A and this system B. I'm going to turn on, so to do an interference experiment, I'm going to turn on for a suitable time a Hamiltonian that looks like sum over sites in the system. Let's call the sites I, AI dagger, B sub I plus AI dagger. So this is kind of, right, so this is hopping between the two systems. And this is the same as actually a beam splitter, right? I have my bosonic atoms. It's a little bit like taking, for each of these sites here, it's a little bit like taking 2 photons and putting them on a beam splitter. Okay. And so now, we could draw it kind of like this. I have some mode that I'm calling A, which would be horizontal one, a mode that I'm calling B. So I can do sort of a mapping to a case where I have 2 photons incident on the beam splitter. And so just sort of as a question, imagine that I had exactly 1 photon incident on each port of the beam splitter. So like my psi in is 1 in mode A cross 1 in mode B. So this would be an example of an unentangled state that I could, so this would each site, let me say that again, this would be a case where each site is in a pure state. So again, these 2 ports are representing 2 sites that I'm interfering. Each one is in a pure state. Can anyone tell me what I would get out of the beam splitter in this case, of the 2 ports of the beam splitter? So like my input state is these 2 ports. Anyone know what the output state would be? Okay. You're not all quantum optics people, so yeah. So in the field of quantum optics, there's something known as the Holographic effect, which is that actually the output, so I evolve for a suitable time under this Hamiltonian to implement this beam splitter operation. The output is going to be that I have exactly 2 photons out of one port and 0 photons out of the other. So I either get both photons out this port or both photons out that one, and I never get 1 and 1. Is this something you've seen before? You can convince yourself, you can do the algebra and convince yourself. But this is kind of a neat fact about boson subject to this type of a beam splitter operation, is that if I look at the number of photons out of a given port, in this case where it's 1 and 1, I always get 2 out, 1 and 0 the other. But more generally, if I send the same Fock state into these 2 ports of the beam splitter, you're actually always going to get even parity of the photon number out of each port. So you're never going to get an odd number here and an odd number there if the input state is pure, actually. And so it turns out that the parity, it turns out that the, so if I define like the parity as the like -1 to the number of photons in one of the ports at the output, this parity operator is actually a measure of the purity of the quantum state that went into the beam splitter. If I have even parity, that indicates a pure quantum state. If I have odd parity, the only way that can happen is if I had a mixed state. And so actually just by measuring in their experiment, just by measuring, interfering these two systems and measuring, do I have an even number or an odd number of atoms at the end in one side, they can actually, and so they can do that in many experiments, they can measure the expectation value of the parity, and that directly gives them a measurement of the purity of the quantum state, and they can do that for a single site, or they can do that for some subsystem. Questions? So if we go back to this picture, this actually allows them to see that, for example, if they, so they can look at the parity for the entire system, right? And even parity, flipped by accident. Even parity would mean that the entire system is pure. And more generally, and the expectation value of the parity then tells them how pure this state is. And that's then closely related actually to the second Renyi entropy. Did you all talk about entanglement entropy? I think there were some things in Slack, so I think you talked about entanglement entropy. So the second Renyi entropy exactly is sort of a first approximation and the bound on the entanglement entropy, and they can get that directly by measuring the purity, which is trace rho squared. So yeah, and so this gives a way of seeing these things like that the system locally is in a mixed state, but globally is in a pure state. So that, you know, okay, so it's maybe worth mentioning, so this is one really kind of, I think, really elegant way of measuring entanglement. It's something that you can't sort of do in, you know, necessarily in every kind of physical system, because again, you need to have these two copies. So one other kind of approach that's been taken in a couple of experiments goes back to this idea of using sort of randomized measurements. So earlier, last time we mentioned something about using randomized measurements as a way of probing the out-of-time order correlation function. But also in similar experiments, it's been possible to basically have something where you have just a single copy of a system. You let it evolve under time. And then you perform some sort of a random operation before you measure, which basically is a way of kind of measuring in some randomized basis. And so in that kind of randomized basis, you can ask questions about what are the correlations between the probabilities of different measurement outcomes. And that actually is an alternative way of being able to quantify entanglement. And so this is, or to get a measure of entropy and entanglement. And as a result, actually similar things have been done with this type of measurement scheme in systems of trapped ions, where like in this picture here, you can kind of see this is again something where they have now a chain of 10 ions. They can see that for 0 ions or all 10 ions, the entropy, the Renyi entropy of the system is quite low. But at some intermediate point where they cut the system in half, the entropy is higher, and that's quantifying the entanglement in the system. So, and you can be fancier and ask questions about mutual information between the two halves. These are all things you can then get out of this type of measurement. So I think this is kind of neat, this sort of toolbox that's developing for directly measuring entanglement in quantum systems, partly because I think it would be really awesome to start to connect this to some of these ideas about entanglement being related to geometry. So I'm not aware of this being done, but my understanding is that in cases where you have a system with a holographic dual, There's a connection between entanglement and the boundary system, and the area of some curve in the bulk, I guess length in this picture that's drawn here. And so I kind of wonder, are there situations where you can have a system at a critical point that might be described by a CFT, where you would expect to be able, by measurements of entanglement, to kind of learn something about this bulk geometry or verify something about this picture. So I don't know if anyone here thinks that's interesting or useful, but it seems to me that this is a toolbox that maybe could be connected more to gravity this way.
Can I ask a question about that? So you showed, I think it was maybe your first talk, where you did these really cool experiments where you had these kind of spin chains that you could create a geometry out of.
Yes, yeah.
So I was curious if, I can't remember if you said you had been able to realize some kind of like a hyperbolic geometry, so something like ADS. You know, it seems like that would be a really great place to try to do exactly this experiment. You could try to use some of those techniques that you just discussed on the previous page and actually, you know, in the lab verify some of these formulas.
Yeah, so maybe I can briefly, I mean, I think what I can briefly say is so what we realized was something, I'll just sketch for a second so I don't have to switch to my laptop, but we realized something where we had a physical system in which the structure of interactions was such that roughly the correlations were well described by thinking of the sites of our system as leaves on a tree graph.
Right, that's right.
And the argument was this tree graph is something like ADS because the depth is log n if the size of the system is n. And in this system, we were, you might recall, actually probing some spin correlations in order to kind of reconstruct that this is kind of this graph is a good picture of the bulk geometry. And we even kind of did some measurements that where like the ideal thing to measure would have been entanglement entropy, but we don't easily have access to that so far in our experiment. At least we haven't sort of worked in that direction. But we did something very coarse, which is just measuring like a correlation function, sort of correlation function between the total spin on this half and the total spin in that half, for example. And the interesting thing to me was that actually even those sort of coarse measurements looked similar, fairly similar, at least qualitatively, to theory for what the entanglement entropy should look like. And so, but I think actually sort of directly measuring entanglement entropy to be able to connect more directly to, I think, to holography seems like it could be an interesting direction. So yeah. And I'm just going to mention while we're on this note, that one of the things I've been kind of curious about is to the extent that there are sort of other measures that signify entanglement in experiments. Are those useful or not? So for example, one thing that I like to think about is sensitivity of the system to perturbations can actually tell you something about entanglement and the number of particles that have to be entangled, because there are fundamental limits to how precise a measurement you can perform without entanglement. And so entanglement enhanced sensitivity can, enhanced sensitivity to some perturbation can be a witness of entanglement and a quantifier of the depth of entanglement. That's not something that is maybe as often connected to these ideas of geometry. Can it be connected? I think there might be a little bit of work on that, but sometimes that's the more natural thing to measure in an experiment. So to me, that's kind of potentially an exciting direction, is connecting sort of other witnesses of entanglement to geometry, if that's possible.
Thank you.
Yeah. Okay. So good. So this is just, I don't know, maybe trying to inspire you all to think about what should we be measuring with this toolbox. Good. So I had this very ambitious plan for the week. You know, I talked a fair amount about measuring information scrambling. We've now talked about measuring entanglement. And one thing we've seen is that actually some similar tools are useful for both. Having two copies of a physical system that you can interfere with each other or that are entangled, having the ability to perform kind of random unitaries. Those are both sort of valuable tools that have been applied to some of these topics. And we talked about teleportation for decoding Hawking radiation. A couple of other things I promised to comment on. we're, so far this is kind of adopting this holographic approach to connecting quantum information with gravity, or taking ideas from gravity to understand quantum many-body systems better. There are a couple of other approaches that are being explored in the lab that I at least want to sort of touch on. So I thought I would say a little bit about, just kind of highlight some recent experiments that look at analog gravity. So for example, can you realize Hawking radiation in an analog system where you have an acoustic black hole, and precision measurement. So I'm just going to kind of touch a little bit on ideas that are out there and things that people are doing, just to give a flavor. So yeah, so we talked about sort of the quantum information approach to thinking about Hawking radiation. The qubit gets scrambled. Can you unscramble it? Can you decode that information? It's worth pointing out that there are other experiments which are pursuing a line of research that was first proposed by Unruh, which is basically, can you realize acoustic analogs of Hawking radiation in the form of phonons in some kind of a fluid. And in fact, one can even do this in a quantum fluid by using a Bose-Einstein condensate. And so there's a series of experiments that were done over the past few years in the group of Jeff Steinhauer, where he essentially prepares a Bose-Einstein condensate in a potential which has a step in it, and actually he can also kind of accelerate the Bose-Einstein condensate by moving its trapping potential. And this sort of acceleration against this step gives rise to something that looks like a horizon. And this is something where they can actually see some excitations that they interpret as Hawking radiation, which essentially can form some kind of patterns in their Bose-Einstein condensate. These patterns have to do with, I guess there's kind of a picture drawn here of these excitations kind of bouncing back and forth between an inner and outer horizon. And so by looking at essentially correlation functions in their density correlations in this condensate, they can sort of probe this analog of Hawking radiation. And there have been various kind of, as I said, there's a series of experiments that they've done where they ask things like, can we probe the temperature of this analog Hawking radiation? Can we actually probe entanglement between the Hawking radiation and entangled partners? And again, this is all by sort of measuring correlation functions in the Bose-Einstein condensate. So this is, I just kind of want to sort of mention, if this is a line that's of interest to you, there's a nice sequence of papers by Jeff Steinhauer that goes into that. In kind of a slightly different approach, also employing a Bose-Einstein condensate, there was the idea, can you study the Unruh Effect? So have something that looks like an accelerating reference frame that gives rise to Unruh radiation that's analogous to Hawking radiation, at an effective temperature that depends on the acceleration. So can you realize some version of that effect? And the sort of rough approach that was taken here was that if I have a scalar field in an accelerating reference frame, then one can show that that's sort of equivalent to having time evolution under a Hamiltonian that involves creation and annihilation of pairs of excitations with opposite momentum. The Unruh radiation, and they kind of are able to actually realize this Hamiltonian by having a Bose-Einstein condensate with an interaction strength that can be dynamically modulated. And I think there's kind of beautiful pictures that they take where, as a result of this modulation that allows them to engineer this Hamiltonian, if they look sort of after some time, take an image of the density of atoms, they see these kind of jets emanating outwards, which are coming about from this sort of creation of pairs of excitations of opposite momentum. And they can actually analyze things like the statistics of the number of particles in these jets to say something about their effective temperature and relate that to the acceleration that they have simulated by kind of engineering this Hamiltonian. And let's see. And they even actually, one kind of neat thing that they're even able to show is that they can reverse this process. And so it really kind of shows something about the coherence of the process. They can actually sort of evolve backwards in time by changing the sign of their Hamiltonian and see that this sort of these outward emanating jets actually start to kind of go back into their central cloud. So this is, yeah, kind of a totally different approach that's not the, you know, connecting quantum information or thinking of sort of a black hole in terms of a scrambling operator and qubits, but asking more, in this case, can you kind of engineer a Hamiltonian that looks like this field that's in an accelerating reference frame? Okay, so that's kind of one other experiment that's going on in the group of Chen Chin. I'll just pause here. That's kind of all. I wanted to just give a flavor of these things so that if you're interested, you can look at them in more depth, but I'll just pause here and ask whether there are any questions about that. Okay, so the last thing that you might want to do is kind of directly probe quantum gravity by precision measurements. And here, I mean, generally the challenge is having systems that are both massive and somehow behaving quantum mechanically. Just to give a flavor of sort of ideas that are out there, one thing that's been proposed is to test for sort of modifications to the commutator between position and momentum that are proposed. I understand that various types of modifications are proposed in a variety of different kind of theories of quantum gravity. And so the idea is, can you sort of do a precision measurement of this commutator in order to check, is it really IH bar, or are there some correction terms that might depend over, let's say, the momentum over the Planck momentum, or with some kind of parameter that says how strong is this correction, right? And to kind of give a sense in this proposal for sort of starting to probe this type of thing, they pointed out that like any bounds on these are actually extremely loose based on any current experiments. So if this beta parameter is kind of so basically if this beta parameter is large, that basically means that these are kind of very small modifications, right? Sorry, did I say that right? If there's so roughly you would like to be able to get to this beta parameter being of order 1. And right in the experiment so far, you're sort of 30 orders of magnitude away. And so, so I said it backwards, sorry. This beta parameter being large means you would only be able to detect an extremely large modification, right? So to be able to detect something that's sort of on a natural scale for Planck scale physics, you would want to be able to have this beta parameter be order 1 and be sensitive to it. Okay, and so roughly this is a modification to the commutator, would also be some modification, of course, to the uncertainty relation between position and momentum. And so roughly the kind of concept here is actually, well, if you had some kind of a massive system that you could displace around, let's say, some loop in phase space. So here it's some loop and position and momentum. Then if you can do this with some ancillary system, which is light, actually, in this case, what you would like to do is some kind of interferometric measurement that actually allows you to measure the fact that there's a geometric phase associated with undergoing this loop in phase space that actually depends on the commutator. So that's kind of the general concept, is that the commutator dictates a phase that would be picked up when you sort of drive the system around this closed loop. And the idea is if you can use light to do this, so you need to kind of have a sufficiently strong effect of this massive system from the light field. And ideally the massive system should be in its ground state, right? So that I can kind of probe a relatively small loop with a small effect from the light. Then the idea is basically that I can do an interferometric measurement on the light field that generated that loop in phase space and detect some phase shift of the light that tells me something about this commutator, right? So this is the phase space of the oscillator. This is the phase space of the light. And the light would pick up some phase shift as well as some squeezing that is sensitive to this commutator. So that's not an experiment that's been done, but I think it's kind of an example of, first of all, sort of thinking creatively about what could you do to really try to get into a regime with what look like somewhat realistic parameters to be sensitive to testing theories that would modify the commutator. So it's also kind of, this is an example of the type of proposal that's motivating people to work on getting massive systems into a well-controlled kind of quantum regime. And there's been kind of, a flurry of different experiments over the past kind of 15 years or so, trying to take massive objects and get them to kind of lower and lower temperatures, closer and closer to their quantum ground states, and in fact, into their quantum ground states. And there's kind of a wide range of physical systems that people work with, ranging from small, fairly light little membranes, all the way up to the mirrors of LIGO. And so, this is actually a plot that the reference will be on a subsequent slide. But this is taken from a recent paper that actually cooled the differential motion of the LIGO mirrors down from room temperature all the way down to an occupation of 10 phonons. But they also kind of show a sort of an array of like what are the different physical systems that have been cooled sort of towards the quantum regime, or that have been cooled particularly using effects of optically sensing the mirror motion, and either via coherent feedback induced by the light field or by some external feedback based on a measurement using the light field, cooling down the motion of the mirror. I just, for myself, I kind of made a line of the Planck mass because I thought maybe that's an interesting reference scale. A couple of things that have been done here. I opened this paper and I was shocked that it showed an experiment that I did as a graduate student, which was really just actually cooling the center of mass motion of a cloud of atoms, but using similar techniques to what some of these experiments that are trying to cool more massive objects. I was amazed that even was worth mentioning on this plot, because we have other ways of cooling atoms. Yeah, so what are the kinds of approaches that people are taking? Here's an example of an experiment that somebody actually mentioned on day one of this week, where this is from the group of Markus Aspelmeier in Vienna. And they are working currently with sort of little nanoparticles on the 100 micron scale, developing some techniques that they hope can also be scaled up potentially to even more massive objects. But the basic idea is that they optically levitate a microsphere, and they cool it using a technique known as cavity cooling. So in my field of sort of laser cooled atoms, the sort of standard cooling technique relies on the fact that atoms have very well resolved spectral lines. Here you have this, this big bead. It's kind of a messy object, although you take care to have it be a high quality factor mechanical oscillator. And what you can do is have something where essentially it's optically trapped. So you can kind of think of it as a harmonic oscillator that has some quantized energy levels. And what you would like to do is sort of drive some process with light that preferentially lowers its energy in this harmonic potential. And the trick that they employ is to have the beads trapped inside an optical resonator. And they can draw, let me actually draw kind of a separate picture for a moment just to kind of illustrate kind of the thing they do. So they have, this is the sort of, there's some resonance associated with this optical cavity. And they have a laser beam that is tuned away from resonance by essentially this vibrational energy of the harmonic oscillator. So the idea is that what you would like to do is have a process where you absorb kind of a lower energy photon from the laser and emit a higher energy photon. So that means you would like your kind of laser field to be tuned to the red of this resonance by an amount that is, I guess in this case, they call it h bar omega x. So that's they're trying to cool the motion in the x direction, and omega x is the trap frequency in that direction. And so the idea is then, because of this resonance feature, the atom will preferentially, it's not an atom, sorry, the bead will preferentially emit a photon that's of a higher energy than the light that they're sending in. And so they do this, and they send in light, the photons get scattered into this resonator, overall higher energy photons get scattered in, and so correspondingly, the energy sort of goes down this ladder of oscillator states all the way into the ground state. Okay, and so that's one way that you can start to get a somewhat massive object into its quantum ground state, as they did in this paper. At kind of another extreme, or sort of an even higher extreme of mass, there's a very recent result using LIGO, actually. Actually, I'm curious, so I know you had lectures on gravitational waves this week. I don't know whether they were more on the theory side or the experimental side, but presumably LIGO was at least mentioned. Did you talk much about how LIGO works, or a little bit? Okay.
I think,
yeah.
I think.
Yeah. So
will
I
come up.
figured we'd at least see LIGO. So, and so here, they have effectively a 10 kilogram oscillator. Their oscillator, they define some mode that's kind of the differential motion of the mirrors, right? What LIGO is sensitive to. And they're basically cooling that, that motional mode. It has an effective mass that's 10 kilograms. And I mean, quite amazingly, they're able to cool this from room temperature down to 77 nanokelvin. So it's just, the mirror isn't at 77 nanokelvin, but the one relevant motional mode is at 77 nanokelvin, which corresponds to having just 10 phonons worth of energy in this mirror. And you can imagine this is hard, right? I actually should have, I guess we can kind of see it here. So the displacement sensitivity they need sort of on a time scale of a second, they need to be able to measure the displacement of the mirror to something on the order of 10 to the minus 20 meters, right? So extremely precise measurement. And there are so many things that go into this, from having basically, so what do you need to do? First of all, sort of you need lots and lots of light, because otherwise you'll be limited by just the statistical fluctuations in the photon counts that you get, right? So they send in a high power laser. They also have the ability to kind of recycle the power to amplify how much power they send in even more. And then they have these resonators in each arm of the interferometer to build up the power yet more and to amplify kind of the information they get out in the phase shift of the light. And then on top of that, as you perhaps learned in some discussion of LIGO, they squeeze the light to reduce that measurement imprecision that you get from the statistical fluctuations even more. And so with all of those ingredients that were just developed even to detect gravitational waves, it's now possible to detect the motion so well that they can feed back on it and cool it down to this extraordinarily low level. So I think there are kind of different, I can imagine there are different things you might want to do with different physical systems, ranging from really massive mirrors to something like these little beads. The little beads, there's the hope that you could kind of prepare them, let's say, in a quantum superposition of two different places and directly do interferometry with this massive object itself, or something like the proposal I pointed out before, measure the commutator using light that interacts with the quantum system. And maybe that's something that can also be done in LIGO, although they probably have other more pressing things on their minds. But yeah, so although I guess, yeah, actually, so once you have a massive system like this that's in the quantum regime, building some additional interferometric measurement to probe it maybe is not so crazy. So, so I think I'm kind of amazed at just the progress that's been reached here with this huge object being so close to its quantum ground state. So I think things that sort of seemed crazy not so long ago in terms of having massive systems in a quantum regime are becoming closer and closer to reach. So one last thing that I'll just mention from the field of cold atoms is that atoms are not Planck mass objects, but they do have a mass. and they can be used to perform kind of exquisitely sensitive measurements by creating them in, so here it is possible to create quite a large quantum superposition of an atom in one place and an atom in another place. And so that's another approach that's being employed to say you can basically use a pulse of laser light to place an atom in a superposition of, let's say, staying where it was or getting a momentum kick in some direction. And so here's kind of an illustration of actually an apparatus in the lab of my colleague Mark Pasovich, who has a 10-meter tall tower where they do these types of atom interferometry experiments, kind of have an atom that is tossed in a superposition of being here and being tossed up. And they can get to the point where actually by having kind of multiple momentum kicks applied in sequence, they have atoms that each individual atom is basically in a superposition of being in one place and being half a meter higher up. So that's kind of a pretty big separation for an object with some mass. This is kind of, there are some measures of sort of how macroscopic is the superposition that have to do with both the mass and sort of the distance scale. Depending on some kind of parameter that folds in both of those, one can, if you can kind of coherently recombine and see interference, you can rule out certain theories of whether gravity might cause superposition states to collapse. I can't say much about how well motivated those theories are, but they're definitely out there. And this type of experiment is kind of a neat way to test and rule them out. Also being used for things like if you have two different masses of your atoms, you can test the equivalence principle. They have recent work on that. So yeah, one other kind of system for probing gravity with quantum techniques. So with that, I guess I actually went faster than I thought I would because we still have a few minutes for questions, but maybe that's good. So yeah, I've kind of, just to sort of summarize, I've shown these different approaches to exploring kind of the intersection of quantum mechanics and gravity. I spent a fair amount of time on kind of the simulation approach that's inspired by the holographic principle. Can we study black holes through the lens of entanglement, and more broadly investigate this concept of gravity or space-time curvature and geometry emerging from entanglement. We gave a sort of very brief overview of what's going on in analog gravity, acoustic analogs of Hawking radiation, for example. And then we touched on precision measurements. Can you really directly probe gravity and quantum mechanics in a regime where they both matter, just by exquisite control over massive objects and high precision? So with that, I will stop and take questions.
Thanks a lot, Monika. Let's thank Monika for the wonderful set of lectures. Yeah, so we got plenty of time for questions. We also have a Q&A tomorrow, so you can save your questions for then. Yeah, so but let's see if there's quick questions now.
For the slide where you showed the experiment of the commutator, measuring the commutator, for that first slide.
Sorry, just a quick comment. That was a proposal and it's not an experiment that's been done. Go ahead.
Oh, okay. Okay, never mind then. Yeah.
Did that already answer the question?
The question was where the data point is on that like left-hand plot. I think the slide before.
Yeah. So that was, and I guess they kind of thought about like, how well has this been ruled out so far? And the answer is not very well. But yeah, it's not an experiment yet. And I showed it kind of just to motivate what's something you might do once you have these kind of well-controlled massive systems in the quantum machine.
Okay. Thanks.
Do you know the theoretical framework that gives them this commutator? It's sort of hard to.
No,
yeah.
Unfortunately, so if you look at their paper, they actually have probably at least 3 different possible models for sort of the form in which the commutator might be modified. And they scale in different ways. They reference a whole bunch of papers on which, what type of model would predict what type of modification. But no, that's something where I would refer you to this paper for more details on. Yeah. Although maybe I'm curious, does anyone here know?
Yeah, does anyone here know? I do not.
Okay, yeah. Oh,
I mean,
yeah.
it's just, I'm skeptical. I'm a little skeptical of the claim that this parameter is so weakly constrained because, you know, I'd have to see the theoretical framework to see what predictions it makes and whether there are actually some other predictions that are completely in conflict with the experiment. But knowing nothing, I shouldn't really say anything. Just
Yeah.
I don't know what the theory is behind it, but I just
on.
looked up there's some recent 2020 paper where they say the form of this beta expression is like important. Basically, some of them don't give a minimum length scale and some of them do. So I'm sure they accounted for that in this paper, but yeah.
Okay.
It has to do with the minimum length scale is the basic idea.
I see.
But I don't know more
I
than
see.
that.
Okay. All right. So then, yeah.
Oh yeah, and I guess actually this thought I think was kind of getting at that somehow like the standard commutator would set one minimum length scale and that would be modified because of the modified uncertainty relation. I'm understanding that correctly. So.
Mm.
One other thing I wanted to say, just kind of while you're thinking about your questions, a bunch of you put really interesting questions actually into the Slack chat during the first lecture. And I have to admit, some of them I understand, and some of them I said, oh, I'm going to have to like read up on that term to even understand exactly what the question is, because as I warned you from the outset, I know more about the lab than about the quantum gravity side. So, but I will try to take another look through that list and see whether that might raise some interesting topics for kind of discussion tomorrow. And I would also be happy if any of you want to maybe elaborate a bit on some of the ideas that you put there, because I think that could be a lot of fun.
That's a great idea. Yeah.
And I will say part of sort of what I was hoping by sort of being in the summer school is that I feel that somehow there are opportunities for dialogue between those of us who do experiments and those of you who kind of think deeply about the theory. And unfortunately, it's really hard to kind of know both sides, right? And so even just sort of developing a common language and for you all to sort of understand something about what's possible in experiments now, where are they kind of moving and what might be possible soon, hopefully that gives you an opportunity to kind of think about what should they be doing, because we might not know, right? We spend so much time just building the tools that we don't get to think about the deep questions as much as you do. So, yeah.
So I'll ask a question. So I think many of the experiments that you showed, roughly speaking, had some number of qubits of order maybe 6 or something like that, and then sort of the NISQ era is meant to be qubits of order 60 to 100. Is that just experiments are waiting to catch up, or there's some fundamental issue with going to 60 or 100 qubits and doing these kinds of experiments on that system?
Yeah, so I think there are different physical platforms that we can talk about. One of them that's maybe a good example are superconducting qubits, because there I did show one experiment that was 53, and that's on kind of Google's state-of-the-art platform, where they also did their famous quantum supremacy experiment, right? So that's kind of, I think, in the regime that you would call this NISQ era. It's kind of just that regime where it's hard to calculate things, or impossible, or you can argue about how many weeks it would have taken to calculate the thing that they did, or years, or eternity, but it's definitely in that regime. So I guess the issue is, Google has that processor, and they have one, and I think that will start to probably become more common. But obviously, that was a huge effort to build, and there's not a lot of not a lot of platforms that are at that stage right now, right? So other people who don't quite have the Google processor, nevertheless, can do some smaller scale things. Now, of course, actually, I think. And there was one example I gave from the Berkeley group with superconducting qubits. I didn't go into detail, but they did one of these decoding the Hawking radiation type experiments with just a small system. So yeah, I think part of it is just that even in this NISQ era, the sort of state-of-the-art tools are really, there are just a few kind of experimental systems that are at that level. In trapped ions, I showed some experiments in chains of like 6 to 10 trapped ions. And they're scaling those up. So those chains have they have very good high fidelity operations. It turns out that there are just challenges in terms of the electric fields that you need to sort of make a longer chain and still have it be not buckle and things like that. So there's definitely work going on that. They also think about modular architectures where you can have several sort of units and they're connected to each other in some way. I think state of the art is probably on the order of 50-ish ions, but that's something that most of these kind of more physicsy experiments are sort of, let's use the system that's sort of well developed that has 6 to 10 ions. And I would probably the larger systems are more focused towards like really what do we need to do to turn this into the best quantum. So
you can't. Sorry,
I want to mention one more platform, which is neutral atoms, which I think is something where there's really been rapid progress just over the past few years. In array, let me actually, sorry, I'm gonna switch to my laptop again just so I can show a pretty picture. Which I probably showed once before, but screen keynote. So I think somewhere I showed some pictures of, oh, this isn't even the best one. Okay, well, here we go. Yeah. Pictures of arrays of neutral atoms. These are 1D arrays, these are 2D arrays, and the state of the art that I didn't show here is probably like maybe 300 atoms in an ordered array. And they also have very high 2-qubit gate fidelities. And so these are, the approach with these systems where you have these atoms in individual tweezers is you excite them to Rydberg states, and those sort of when they're excited, they have a long range interaction so that neighboring tweezers can kind of talk to each other. So that's a system that is very scalable, and they've shown, again, quite high fidelity gates. It doesn't have the issue of ions where it's sort of hard to make a bigger system because you can arrange it in 2D, and that naturally sort of gets to hundreds.
I can't see anything on your
Oh, I'm
screen.
so sorry. I must have, it says I'm sharing, but I must be sharing the wrong thing. So let's just try that one more time. So we do play in window, and then I need to share the window in which it's playing. Can you see it now? Okay, yeah, so
Yes,
just showing these arrays of neutral atoms. And so that I would say for some combination of kind of fidelity of the operations and scalability just has really been taking off as a very promising, exciting technology. So this would be for doing kind of spin type models. And then if you want to do something more like Hubbard type models where you have either bosons or fermions hopping in a lattice, then that's also possible with large numbers. The one example I showed of sort of Hubbard model physics was this measurement of entanglement entropy. And that has the problem that the sort of fidelity of that measurement goes down exponentially in system size when you do this. If you have any imperfection, this interference between the two copies has an exponentially decaying fidelity. And so that's what, even though they can make quite low entropy large systems and look at them at the single particle level, this example of looking at entanglement entropy with two copies, that would be hard in a large system. But there are other, and this is again, we're sort of thinking about what are the observables. Are there simpler observables, correlation functions that can reveal some of the same physics? Are there interesting things to look at in terms of like a system like that at a critical point connecting, you know, is there a situation where there's some connection to ADS-CFT? I think there might be some opportunities there in a regime where you can't calculate things, right?
Yeah, okay. So you kind of think it's a matter of time.
Yeah, I think that's right. Yeah.
A couple of years, maybe. What's the time frame?
Maybe the question is for what? So if you say what you want, what exactly you'd like to see, then.
Well, okay, this teleportation experiment with more than 3 qubits.
Yeah, I think that's probably a matter of time. It's sort of like, again, they measured things like the scrambling of this 53 qubit circuit, right? they, in that case, I mean, actually, you could imagine in a system like that, they probably could make a set of entangled EPR pairs and then do something, something along those lines. Again, it's probably an issue of kind of priorities.
Priorities, yeah,
right?
yeah.
They might rather like implement a quantum algorithm than
Right. Sure.
study
So
quantum
yeah,
gravity. But
we'll wait
I think,
until
yeah,
we'll wait until they move on to the next system and then
Yeah,
use that. for black holes.
exactly. Yeah.
Very good.
So great. And any last questions?
Any other questions?
So if not, again, I'll look some more at your comments from day one as sort of maybe a starting point for discussions on Friday. So yeah, please bring questions and ideas of what might be cool to do in future experiments, and I hope that we'll have a nice discussion tomorrow.
Okay, thank you very much, Monika.
Yep. Bye.